Hello, welcome back. In the previous segment, we defined what is a field. In this segment, I will define what is a finite field. A finite field is just a field which has finite number of elements. Okay. So in the previous segment, we talked about infinite fields essentially, we talked about set of all real numbers that's infinite. But in cryptography, we almost often deal with finite field. Okay. So finite field is made of finite number of elements, and there is a terminology for it. It's called order. Order means the number of elements in a field. Okay, we call it order. Okay, so if I say order of the field is m, it means there are m elements in the set of the field f. Okay, so if you have a field f, and if the number of elements in the field is m, then that is called the order of the field. Okay, so there is an important theorem in finite field. We will not prove that, but we will make use of the theorem. The theorem says that it is possible to construct a finite field as long as the number of elements in the field is written as m equal to p power n. Suppose you know m, you know p, and you know n. As long as m can be written as p power n, right? It should be possible to construct a field f of order m. Okay. N is a natural number, of course. N is even more precisely, n is greater than 0, so it's a positive number. P is a prime number. Okay, we don't know how to construct it, but the theorem says there must exist a field if the number of elements in the field is a prime power some integer. Okay, that is the theorem. Let's take a simple example. Let's take n equal to 1. It's an easy scenario. It means your m is just p. Okay, can we construct a finite field with p elements? The answer is yes. How about zp, which is set of all numbers from 0 through p minus 1, right? We already saw this set forms a group under plus, and if you throw 0 out, it forms also a group under multiplication. Okay, when you multiply two numbers, the answer is within the zp. Of course, you need to do mod p, right? And since p is a prime number, inverse exists for every non-zero element. So all the properties that are needed for multiplicative group is true. Similarly for addition as well, if you keep 0 as identity element. So we have multiplication, multiplicative group, additive group, and then we also have, of course, the distributive property. Okay, you could take any three elements a, b, c from zp and mix multiplication and plus in this order with a times b plus c is same as a times b plus a times c. This is just because of the definition of mod p. We already talked about mod. Mod satisfies this distributive property, so I don't have to prove it again. Okay, so zp itself is a finite field. Okay, it's even more precisely called prime field because p is a prime number. All right. And it satisfies the theorem that I talked about, right? P is equal to, P is the number of elements in the field. So n, if you put n equal to 1, you get m equal to p. So the order of this finite field is p. Okay, according to this theorem, if m equal to p power n, then there must exist a finite field with m elements. Okay, we put n equal to 1 and we constructed a prime field. Okay. But in cryptography, we also deal with other types of fields, not just fields made of numbers. So in the next segment, I will talk about extension fields and define it more formally, precisely over there. For now, it's good enough to know a finite field means it's just a field with finite number of elements. The order of the field means the number of elements in the field. And the theorem says that if the number of elements in a field is p power n, okay, suppose you give me a m, which is p power n, then I must be able to construct a field of order m. Okay, the theorem doesn't tell you how to construct, but the theorem says there must exist a field f of order m. Okay, that's all. So let me quickly formally type the theorem. Okay, the theorem says as follows: a field f with order m exists if m is equal to p power n. Okay, this is not to be confused with XOR. This is p power n. Okay, of course, I mentioned n is greater than 0 and p is a prime number. Okay, this is the theorem that I used to demonstrate with the case n equal to 1. Okay, and constructed a prime field for you. All right, that's basically it. And I will show you the extension field in the next segment.